So, similarly to the Autobike project, we also have an outline for our presentation. We will begin with going over the background, the previous iterations, the goals and the tasks we derived from those goals, the results we found out, we got, our conclusions, and also suggestions for future work. So to begin with, the background. In Sweden, on average, every person creates around 440 kilos of refuse each year, and that needs to be handled. Today, that means garbage trucks would need to drive into housing areas to pick up garbage, either from individual bins or from small, somewhat centralized collection areas. However, those centralized collection areas can't be too far away from the housing areas or from the homes, so people will still be able to walk there, or willing even. The Unicorn project envisions to streamline this system and allows centralize the garbage collection even more. By using a fleet of small autonomous robots that are able to walk further between the station and the homes, it is possible to put the stations further away. By using small robots, and thus quiet robots, it will also be able to drive all day and all night with minimal disturbance for the people living in the residential areas. The Unicorn project spans 3 years. It began in 2017 and is a collaboration between multiple partners. Those partners are Chalmers, which manages the entire project and also develops the scheduling for every single system. It's PWS, which will develop the bins and the centralized station. Hiab, which will construct the autonomous crane, which will fit on the Volvo trucks. Gothenburg City, which will provide an area for testing. Volvo and Husqvarna will provide knowledge and guidance and will assist with development. And finally us at MDH, which develops the autonomous robot. The Unicorn project owns its heritage to Project ROAR and the conclusions drawn from that project. In short, the goal of ROAR was to optimize garbage collection by mounting a robot on the back of a garbage truck, which will assist the driver of the truck to collect the bins. Although successful, that robot was big, it was slow, it was loud and noisy, and thus the Unicorn project was born from that. In the previous years on the project, they created Charlie. She was built on the Husqvarna Automor 430X, and by the end of the project, they had the robot which could localize, navigate, and avoid obstacles indoors. Some of the future areas that were pointed out that needed more work was communication with the control tower. Refuse collection hadn't been figured out, and how to show intention to the rest of the world what the robot was doing. So in this iteration, the goals are to create an autonomous robot or continue building it. The navigation in unknown environments still needs to happen. To collect and handle refuse, it's a central part of this project. Show intention, and to limit the scope of this project, it was decided to work indoors. Although everything that we put on the robot could and should be easily adapted to outdoor use later on. The tasks derived from these goals were to design and build a lift system, to implement ultra-wideband for localization and also the possibility of communication, to explore a solution for showing intention, and to explore TetaStar for path panning. So some general information of the Unicorn in this moment. It is built around the Husqvarna Automor 430X. Main benefit of that, it makes it small, it makes it quiet. A somewhat drawback is that is a unit designed to move outdoors, meaning the wheels are suboptimal and it loses odometer sometimes. The brain of the operations is an NVIDIA Jetson TX2, currently a development board. To make life a little bit easier, we use the robot operating system version Kinetic as a middleware to communicate between the Jetson and the computer in the lawnmower, which controls the wheels, and to our sensors and other actuators. Since we're using ROS, we are stuck in Linux. and we are also stuck in programming in C++ and Python. Now for the mechanical part.
Yep. Yes, so the mechanical department of Unicorn has been focusing mainly on the lift system, and this is to ensure to give Charlie the opportunity to lift off refuse bins from households and placing them securely on Charlie for transportation. The defined maximum payload for Charlie is 10 kilograms, but testing shows that we can at least lift 15 kilograms. Another mechanical achievement is the base plate, which has been substituted from a very thin and wobbly one to a more thicker and more robust one. So the lift system has three main areas: the mechanical motion, the hardware, and the software. For the mechanical motion, we have linear motion to be able to actuate it in two axes. The hardware is basically controllers for the motors and the microcontrollers. And for the software, we use ROS in combination with the Arduino IDE for communication. We've done some testing, and just a brief one is that we've done lifting tests with different weight payloads. So we started at 0 kilograms, and we've incremented with 3 kilograms with each iteration, and done 3 tests on each. And to the right, we can see just how the time increases with weight, just to get an intuitive feeling of how that increases. Yeah. And the parts that has been added to Charlie, as well as the entire lift system, has all been constructed and modeled in SolidWorks. Mainly, we have custom parts, which includes all of the mounting for all of the sensors and peripherals. We'll also have the actual peripherals modeled, which has been designed to look as similar as they do in real life. And also we have the Rollco and advanced parts with which all the for the linear motion and the cog wheels, but they have been provided in an already completed format. Here's a little quick
Tom, for God's sake.
Yeah, here's a quick show of some of the mountings that we have for the peripherals. Where we have the projector mount, which also have like a screwing option, which can tilt the entire projector to provide different angles for it. Rollco, which is one of our sponsors, has provided us with very high efficient linear motion products. This one here. Yeah, this one here are the C-rails, which are important for us in vertical orientation when we lift off our bins. The ball rods, which are transmission for power between the motors and the motion. And we have bearings and ball bearings for smooth motion for the entire lift system to move on Charlie. And now Muji will continue with motion and stuff.
Yeah, so for the lift system, we have the linear motion in the horizontal and vertical direction. To provide that motion, we have used two motors to provide this motion to drive the lift system into proposed direction, and variation of weights in the bin affect the execution time of the motors and and the speed of the motor. To solve this problem for four micro switches are used to and are located into on different position on the lift system to start, stop, and change up the direction of the motors. The picture shows the connection between hardware that are used in the lift system. The power distribution board cannot generate the desired voltage for the motors. Because of this, we use a buck converter to deliver that voltage that motors need. Arduino together with motor shell control the motor, send data to the main computer TX2, and also read data from microswitch through through digital I/O pins. The baud rate depends on how much data received and transferred. In our case, is because it's not that much data, so low baud rate works very fine. In order to be able to communicate with the main computer, two nodes are created, one in the TX2 and one in the Arduino. Each node has its own publisher and subscriber, and both that publish and subscribe in the same topic. Basically, when the ROS master is running, as soon as the node in the TX2 become activated, it will send a message to the lift system, and when the lift system gets that message, it will send an acknowledgement back to the main computer and start to operate. When the lifting is done, the lift system will send another message to the main computer that lifting is done and Unicorn can start to move further. Yeah, here we have some short video on how lift system works. It received the message. The motor change direction or stopped when microswitch pushed. And that's it. Yeah, now Marielle, we're going to talk about her parts.
Thank you so much. So one of the main goals with this project, as mentioned by Ulrik, is to accurately locate the robot in the environment. And we need to send this information further to our control tower that is responsible for giving further instruction to these autonomous vehicles. And this is why it's very important that we have a robust communication channel between the control tower and the robots. And this is where ultra-wideband plays some very important part. So what is ultra-wideband? It's an emerging radio technology that provides accurate positioning and great penetration capabilities. And this is due to UVB operating over a wide range of frequencies while emitting short time pulses. And if we look at the characteristics of these signals, as you can see here on the picture, they are very steep, short, and narrow, and because of that, they are very good at being distinguished even in noise environments. As well as because the UVB also operates just above the noise floor, we don't disturb other radio technologies that operate in the same frequencies. And lastly, what I want to mention is that UVB can also provide centimeter level accuracy, and this is because of it extracting information from the radio signals in a different way compared to other radio technologies that can only, for now, provide accuracy up to 1 meter. So, I'm sorry, that was the wrong way. Okay. So when it comes to the hardware, there's a wide range of UVB products out in the market, but we found some research that shows that products from a company called Decawave provide a more astonishing or better performance when it comes to locating objects in the environment. And for that reason, we decided to utilize the Decawave's modules for this project. When it comes to the software, maybe not everyone knows, but usually you have to have minimum of 2 to 3 reference nodes that we call anchors that you place in the environment, and then you use them. You also have a UVB module that you place on the object that you want to locate, and in this case it's a robot. And then we implemented code in ROS where you distract the distance between all these reference nodes according to the tag, and then you perform something that is called trilateration, which basically is just utilizing this distance, which gives you a radius, which then creates like a circle around the reference node, and then you calculate the intersection between all these here on the reference circles, and then you get the position of the target. But in ROS, there's also a core navigation stack that is responsible for providing the the localization of the robot, but using other sensors such as odometry data and scan information and a probabilistic localization algorithm. But in this project, we also attempted to use all this information together and fuse it together with the UVB pose that we got to even make the robot more accurate than it is today. So lastly, I want to show is a clip where we visualized it, this UVB, and you can see that the tag is the one actually behind. It's first a bit slow at calculating, but as you can see, it still follows the robot quite good, and it's placed, I want to note that it's placed behind the robot. And here's another video that shows what happens when one of the anchors dies and it cannot locate it. It doesn't work. So for future reference, you could maybe use more anchors, like 4, to make it like not behave this way if something were to like disappear. So now Alexandra will talk about human intention. Yeah, you just click. I don't know which one. I think.
So, robot intention communication we can call any method that gives humans awareness about what the robot is planning to do. This issue is important because moving robots can be quite intimidating for humans, raising their anxiety levels. Research shows that robots that can communicate their intention towards humans lower anxiety and provide a more efficient collaboration. The Unicorn project includes freely moving robots that will potentially cross ways with humans on the streets. Therefore, we implemented a method to communicate the robot's intended path. The method we took is to project the robot's moving direction in front of it. To show where the robot is going, we first need to extract the data that is used to set the direction. In ROS, this is called the twist message, which controls the odometry. If we read these messages, then we can extract the robot's speed and its turning direction to show an appropriate projection. There were some challenges with this method during implementation. For the first, the robot's moving direction differs from the overall direction that leads to the goal destination. This picture illustrates the problem. If Charlie is set out to reach this goal, this is the expected path that it should take. But in reality, it gets commands to 10 times a second to turn left and right very fast. It results in frequent changes in direction. So these problems add up to image flickering, but we need to show a more consistent path. The solution we took is to first of all read the direction command messages less frequently than they are published, only twice a second instead of 10 times a second. Secondly, we defined 5 main intervals of possible directions. You can see it on this picture. So if the robot's turning direction is between these two values, we still consider it straight. It doesn't have to be exactly straight. And then we have soft right, soft left, sharp right, sharp left images to show. So now that we can show the direction, the next step is to mount the projector onto the robot. Since the projector lens is not exactly vertical to the projection plane, the image will be distorted. We can correct this by graphical transformations such as rotation, translation, and scaling. I updated this slide recently, so you have to download it again. I want to show a picture where there is the original image and then the distorted images and how you can correct it. That's it. Yeah. Of course. How do I start? In action. This is not important. It's because when we filmed it, it was not full screen. Huh? No. The projection is important. That little thing was not important. Shut up.
Okay. To share the same workspace for human and robot, the robot must able to create a collision-free path from his start position to reach the destination. So we need a path planning module for that. This module create an optimal path by minimizing the computational time and distance that is covered by the robot and avoid the static and dynamic obstacles. So the navigation module having 2 parts, one is global path planner and another is local path planner. The global path planner operates in a known environment and it avoids the static obstacle, whereas the local path planner, it operates in an unknown environment and it avoids dynamic obstacles. Last year project, it was implemented ROSE navigation stack where the global path planner was Distra and the local path planner was time elastic band. This year we decided to change the global path planner from Distra to Theta star. The problem with Distra is it always find the shortest path to every cell in the map. So it is having high cost of computation time, whereas Theta select the neighbor cell from with the shortest path from the current cell. So this is the path calculated by the Theta star from start to goal. And when the robot is moving towards its goal position, it may deviate from its original path that is calculated by the Theta star due to obstacle avoidance. So to able to move the robot towards its goal, static flow field has been generated towards the configured path, and as Theta star is also computationally heavy algorithm, so it will only rerun when there's a significant change in the environment or the robot is far away from the path generated by the static flow field. So if the robot is beyond this path, then we need to run the algorithm Theta star again. So for any global planner to be used with Move base node, we need to adhere with the Nave core package. This package provides an interface for global planner, and here we use ThetaStar as a plugin for the Move base node. And we tested our algorithm, and the result is showing in RViz, where this is the first we run the Carrot planner, which is very simple algorithm. It always find the shortest path from its origin to goal, but it cannot avoid the obstacle, so the path is through the obstacle, which is not good. And then this is the Distra, which created also path, but this path is longer than the ThetaStar, which always find the shortest path. And that's it.
So, to conclude, in this project, I can say that we all have worked on it, has learned a lot. Especially we have had to learn ROS. Only a few of us had actually worked with it before, and that meant we spent a lot of time in the beginning to familiarize ourselves with the system and how to use it. We also can conclude that implementing existing solutions or simply just adapting them can save you a lot of time. However, it could also be a trap, because if you just implement something and are not really sure how it works, when you have to debug it, it's gonna take time. Personally, for me, working in and managing a project of this size and over such a long time is a new experience. And it has been both fulfilling and exciting, but also frustrating at some points where nothing is working and the end seems to be far away. Some difficulties, of course we had difficulties, I would be lying otherwise. The single biggest challenge we had was to take over an existing work. These projects, they are big, they span multiple years and they are worked on for a fairly long time. And to understand what has been done the previous years could be hard, and especially if the documentation is lacking or comments in the code are not where they are supposed to be. So I'm hoping we will do a good job at handing this over to you. Unless you're mean to us with the questions, then you will have no documentation at all. Scheduling your time is also quite difficult, because you guesstimate that something will take half a day, and the next thing you know, it has been half a week and you are still nowhere near finishing what you began with. So that is something that you learn it, but it takes time, and especially in the beginning. Always plan that it takes twice as long as you think it should take. Some suggestions for future work would be to redesign the PDB, the Power Distribution Board of Charlie. We made the choice not to limit ourselves by the current PDB this year. Mainly because we needed and wanted to implement a lot of new devices and solutions which would not work with the current PDB, and being able to pick suitable solutions first and then redesign the PDB after that seemed to be the better solution. Handling the bins. As you saw in the videos, we have a system to move the lift, but I think it was clear that it's really dependent on being in the exact right location for this to be halfway functioning. We have no way as of now to identify a bin and navigate to it, so that is something that you will have to look into next year. Reduce the amount of Arduino controllers could be a good idea. Arduinos, nice as they are for prototyping, may or may not be the best solution for half of the times, but they are since they're easy to test stuff on, it's what we have used, and maybe it should be time to start looking into reducing some of them. Some of the 3D printed items may have been abused a little bit more than we first intended, and looking into either redesigning them or just print copies for them might be a good idea for you. The robot is currently naked and it is not at all suitable to go outside with it. So designing a cover for the robot is a good start to weatherproof it. We're using micro switches for the lift system. It might be a good idea to investigate contact-free solutions for those, to reduce the mechanical wear and tear on them. And finally, it might be a suitable idea to investigate to how to use the dipole flow field as a local path planner, which is an emerging technology here at MDH. Finally, we would like to thank Mikael Ekström and Birgitta Frascher, who has been our supervisor in this project and has supported us and gave us good hints when we are about to do something interesting. We would also give a special thanks to Joaquin Ballesteros, who has guided us through ROS and gave us some lectures with much needed knowledge for us to use. And everybody else at the faculty has been there for us to help us when questions have arisen and give us ideas and work with them. Now for questions, anything. Yes, actually I have some.
I think maybe we should all go